In this video, I'm going to give you a crash course in collision theory and reaction rate. Notice the play on words, collision theory, crash course. I thought it was funny. All right, so here's a chemical reaction. We've got hydrogen and chlorine. They're combining to form HCl, which is hydrochloric acid. So what's going on here? Like, seriously, what does this even mean? All right? Well, a chemical reaction is where one or more substances are changed due to a rearrangement of atoms. Okay, so our reactants are things on the left side of our chemical reaction, our hydrogen and chlorine. The bonds of those reactants are going to break. The atoms are going to get jumbled around and rearranged, and then you'll have new bonds that are going to form. So here's what's going on. We've got our hydrogen. We have our chlorine. So what's going to happen is these bonds here are going to break. The hydrogens are going to break apart, the chlorines are going to break apart, and then new bonds are going to form. So we'll end up with hydrogen and chlorine combining. Those are the new bonds that are forming. And that is, in a nutshell, what's happening in a chemical reaction. Now, chemical reactions will only occur if reactants collide with one another. You have things smashing together. That's the whole collision theory that we're looking at here. All right, so let's define collision theory. Collision theory says the rate of the reaction depends on how often the particles collide and with how much energy. So if you think back to our previous unit when we talked about our potential energy diagrams, you've got this hump, this activation energy right here. That's the hill that you have to kind of get to the top of for the reaction to occur. So think about this. You're a grown adult riding a tricycle up to the top of a hill. You have to have enough energy to pedal your tricycle to reach the top of the hill. Now, if you don't have enough energy, if you get really tired, and let's say you only make it halfway up, you're going to roll backwards and probably topple over. And again, if you're a grown adult riding a little tiny tricycle, that would be pretty funny. Well, the same thing kind of happens with a chemical reaction. If you don't have enough energy when those particles smash together, you don't get a reaction. The other thing that you have to look at is the orientation or alignment. So here's a chemical reaction. We have A plus B and C, and then you're going to end up with A and B and then C. So basically, A and C are trading places. This is a single replacement reaction. So if you look here, A and B are lined up. They collide and they form the compound AB, and then C is kind of knocked off. Well, if the B and the C kind of switch places like this, there isn't going to be a reaction. A and C aren't going to combine. It needs to be lined up, B and C. So alignment is very important. Okay, so in order to increase the reaction rate, we need more effective collisions. So you need to have enough energy and you need to have the right orientation. All right, there are 5 factors we're going to look at to increase the reaction rate. The first one is increasing the pressure or decreasing the volume. Molecules are closer together and more likely to combine when you increase the pressure by decreasing the volume. This applies to gases only. So think about it. If you're a wide open field with, 10 people, your chances of running into somebody are pretty slim, especially if you guys are spread out. But if you take that same football field and you shrink it down to a really tiny closet, your chances of bumping into somebody are pretty big. So when we decrease the volume, we're going to increase the pressure and our chances of bumping in are increased. The next factor we're going to look at is concentration. The more reactant molecules that you have for collisions, the greater the chances are that they're going to bump into somebody. This applies to aqueous solutions, which remember, you're dissolved in water when you're aqueous. So if we have 5 people in a room, the chances of bumping into somebody are okay. But if we had way more people in the same size room, the chances of bumping into somebody increase significantly. The same kind of thing happens. So when we increase the concentration, we're increasing the reaction rate. Another factor is temperature. As temperature increases, so does kinetic energy. If molecules are moving faster, they're more likely to collide with enough energy. So think about this. You're a kindergarten teacher, and you give your kindergarten class a bunch of sugar, right? Now those same kids are not just sitting still. Now they're bouncing around. The chances of those kids bouncing into each other increases. So when you increase the temperature, it's like giving a room full of kids a bunch of sugar. They're going to bump into each other. The fourth factor is surface area. When you expose more surface area, the chance of a collision occurring is greater. This is for solids. So on the right side here, I have some sugar cubes. All right. So the inner part of that cube, the sugar on the inside of that cube, is not exposed until the outer part of that sugar cube were to dissolve in water. But if I took those same sugar cubes and I crushed them into what you see here on the left, like the normal sugar that you would put in your coffee, I should probably have some coffee. If you take that sugar and you pour it into your coffee, the chances of it dissolving faster it's more likely to dissolve faster because more surface area is exposed. All of the sugar is exposed at once. All right, the final factor is a catalyst. A catalyst increases the rate of reaction by providing an alternative pathway for the reaction to occur with lower activation energy. A catalyst can be regenerated, so that means it can remain chemically unchanged at the end of a reaction. Now, you've probably heard the term catalyst used before, right? Catalysts are common. You may have heard of a catalytic converter, right? That kind of uses a catalyst, but let's take a look at what actually happens. So here is a potential energy diagram. The blue line here is the activation energy without a catalyst. So notice here, the reactants are still at the same level and the products are still at the same starting energy. The reactants are at the same starting energy and the products are at the same ending energy. The only thing that changes with a catalyst is the activation energy. So as you can see, the blue here is what is required without a catalyst, but the red here is the amount of energy that is required with a catalyst. So as you can see, it is much lower than without a catalyst. And all that catalyst does is it provides an alternative pathway for your reaction to occur with less energy. All right, it's like a shortcut. And that, in a nutshell, is collision theory.